so unique and so very interesting too. But if it wasn't for so many of the frontline workers, we cannot be doing what we're doing today. So again, just collectively, a thank you to those workers because without them, we couldn't be where we are today. So today's agenda, we will start the project presentations will short very quickly, and it will end around 3:15 from the students. They are divided into different teams. One team may consist of more than one student. They'll be presenting results of an industry project that they've been working on. And again, the definition of an industry project is something that's of interest to the sponsoring industry. They work with the energy industry. We have some very notable industries who have participated. So they set out to solve a problem that's of interest, obviously a business interest too. Please mute your audio, please. So this is of business interest to the industry that's sponsoring these projects. So they have skin in the game, as it were, and students have to display a number of skills, innovation being one of them, presentation being another, execution, of course, being a key part, collaboration. So all the things that one expects to be doing in real life are kind of come forth in this particular exercise. Between 3:15 to 4, there'll be some open questions, though this will be in addition to questions that may come up, during the student's presentation, something that could appear as an afterthought. And so the forum will welcome questions from anybody in the audience. Meanwhile, during that period, 3:15 to 4, you'll also be completing this evaluation sheet that you received from an emailing from Susan. And I'll discuss a little bit more about that, but that evaluation is very key in looking at what you felt were the attributes that they were asked to display. And then we'll have hopefully a welcome break for whatever time we have remaining, when we will go into our Strategic Advisory Council meeting, which is between 4 to 5. And that is only by invitation. And in this period, we talk about progress during a particular semester, specific highlights, and there's no doubt that you'll hear a lot about the extraordinary times that we've been working under, and there's some good news, obviously, from that, and obviously some not so good news because we've been working under a handicap. Well, this program for some people extends for 4 hours. So you can't do 4 hours without stretching and having a break and being off the air. So we'll kind of fight through this. We'll do this together. So please keep your audio on mute, especially if you're not speaking. Students, please don't mute your phone because sometimes you may be on stage and not aware that your audio is muted. If there are any issues, there's a chat feature and it's off to the screen. And this is one way to kind of either share a message between somebody, you and the student, me, or me, you and Susan, or you and the entire audience. So that's another nice thing about this capability. The third major bullet I have is the evaluation forms, which are sent to the SAC members, the industry project managers, who also are in the audience, and special invitees. And that evaluation form, I'll show you a little more detail on that. It asks you to rank what you heard from the students on those 4 categories.
Sounds like somebody's cooking lunch.
or backing a truck or something. All right. So I've had my marker going too now. So these are the four attributes: results, innovation, results, significance. Again, this is an industry-sponsored project, so the result must be significant to the industry. In this day and age, it would mean something like, is it capable of being implemented in the field? And what could the return on investment or ROI or payback, what would that look like? In past SAC meetings, this was a very strong feature that you said needs to be a part of our projects. And I think you'll hear some very exciting things about the projects we've been performing on this past year. The third attribute is execution. And as you all know, any project has its twists and turns and down moments and up moments too, but how the student or the team works on this project to take it to execution and making compromises, obviously, is also a part of a project exercise that they go to. And finally, presentation. All this, how this is presented so that it's understandable to the expert, to lay people, and everybody in between, is also what we try to measure. So, and these are 4 of among 8 attributes. The other 4 attributes have to do with collaboration, how they, conduct themselves in class and so on. So that's, it's not easily open to outside evaluation. I'll show you that evaluation form soon, and I'll talk a little bit more about it. It is available to those who's being distributed to in hard copy or in a Google form. And our advice and recommendation is use the Google form because you can have some free form comments, that observations that you make, and those are sometimes as valuable as the ratings that you provide. So recommend that you look at the Google form, but if you have difficulty accessing it, please use the hard copy form and just send a copy to us. And I don't have to remind you that we live in this world of virtual audience. This poster, we used to call it Poster Symposium, but it's Project Symposium. It was kind of a happy moment, not only wandering to one poster to another, but enjoying a snack or two, but also conversing very informally with the students. We can do a little bit of that, but unfortunately, that part we will not be, we won't go through that experience. And so this is a virtual audience, and so it's a little bit hands-off, but nevertheless, it's got some other capabilities that hopefully we can take advantage of. Here's the project evaluation form. There are 5 teams as shown, and you'll be asked to rank each of the team and the team members on a scale through 1 through 5, 1 being poor, 5 being distinguished, in those 4 categories that I mentioned: innovation, results, significance, execution, and presentation. And I just want to let you know, in the past, the students have been doing pretty damn well. The fall semester, when we had this project symposium, they all ranked consistently in the very high range between 4 and 5. So I'm very confident that I think that you guys would feel the same way. In very small type is the project that they're working on. I'll just give you a quick rundown. Team 1 is working on advanced energy community, which is a follow-on to 2 years of work in which past students have been performing on. It is sponsored by OSI Soft and a startup company, DareNetSoft. Working with the local utility in the San Francisco Bay Area. So Vinny, Emma, and Eric are part of Team 1. Nicholas Vinansky is the single member of Team 2. He's working with PP&L on a predictive analytics for Volt-VAR operation impact. Team 3 is Stan Worthington. He's a US Navy officer. And like his predecessor, he got a promotion while in this course. And he'll be talking about feasibility of retrofitting some used fuel tanks for pumped hydro storage for select US Navy facilities. Team 4 consists of 2 persons, Josh and Nicholas Wagner. They're working on a project looking at solar penetration in PP&L service territory. PP&L is a local utility in Pennsylvania, and they have come up with some very interesting quantitative methods to look at how best to optimize not only the land area, but also the termination areas and the feeder lines, you know, where a solar farm can be hosted. So they'll be talking about that. And the 5th team is made up of Larry Montes. He's working with one of our Lehigh professors in looking at novel ways of cooling buildings using phase change materials. So anyway, I think this, you'll have hopefully this form in front of you as you listen to these presentations, and it'll help you in making your assessments. Open questions, I mentioned this 3:15 to 4 is another area, a time where you could ask questions that probably you weren't able to bring up when they made their presentation. But it's more free form this time period. You'll have a chance to complete your evaluation forms, and we'll have a welcome break, and we meet again, only the invitees at 4 o'clock. This looks like a familiar figure. You probably saw the NFL 2020 draft. That's our commissioner there. And like everybody else, he has a split screen among tons of people. And this was the quote. It says, "The virtual platform has introduced many possibilities." I can't read the rest of it, but it could be used in different ways. Now, you know, it was kind of inspiring because they looked at a potentially tragic event to something that turned out to be terrific. And they just used the technology and capabilities in ways that are, you know, very novel. You know, they're also a business, and they also want to kind of display what the value of that business is. And in some ways, we have some parallels. We are an academic institution, and we want to also demonstrate the value of learning and teaching using a platform that's not completely familiar to us. But I want to take full advantage. I want the students to take full advantage. This is also a learning moment. And we may be forced to doing this for many months. And in fact, there may be some features of it that could be a permanent feature that we wish to follow. So thank you, NFL. I think I was inspired when I saw that, and hopefully you guys will be inspired after we hear the students. We actually had ever since we went into this COVID-19 guidelines, we've had several events in April. One of them was the Energy Seminar Series on Climate Action Plan, which took place last week. It was a 2-hour event. It went pretty smoothly, and we were able to record it, and it will be available pretty soon to the general public. All right, so let me introduce the teams. Emma, Eric, and Vinny are part of Team 1. Team 2 is Nick, working with PP&L on this project on Volt-VAR comparison. Team 3 is Stanley Worthington. He'll talk about retrofitting US Navy assets for energy storage. Team 4 is Josh and Nick Wagner. They'll be talking about solar hosting capacity and ways to visualize and quantify what the capacity, how you could interpret that with PP&L. And finally, Team 5 is Larry Montes. So I'll stop right there and we will introduce team one.
Thanks, Rudy. We'll get started here. Emma is going to be queuing up the slides. Thank you, everyone, for joining. And I hope everyone is healthy and staying safe out there, as well as your families. Emma, are you okay with the sharing? Is it?
Yeah, it says that it's disabled if you're not the host.
Oh, I see. Professor Shankar.
I have allowed multiple participants to.
Oh, okay, I got it.
Okay, great. All right, so again, my name is Vinny Aguiar, and my team members want to have them introduce themselves too, so you can get acquainted with the voices as we move along.
Hi, I'm Emma Hillman.
Hi, I'm Eric Lawati.
And our project that we'll be talking to you today is titled Integrating Electric Vehicle Charging into Distributed Energy Optimization and Aggregation for Advanced Energy Communities. Quite a mouthful, but we hope to unpack all of that for you today. We are working in partnership with DER NetSoft. They are a startup company based on the Bay Area, and they hope to develop or have developed some data analytic tools to help communities adopt distributed energy resources and aggregate these DERs into what we call an advanced energy community. So we want to step through some of the objectives, give you an idea of why this is important, provide some background into the literature review and facts we gathered, then walk you through the methodology of our rating index, and finally close out with a, so what, what's the implication of this? So I'll turn it over to Eric to jump through some of those objectives.
So thanks, Vinny. So like Vinny mentioned, we're working for DER NetSoft, a startup in the Bay Area, and what we're doing is developing a tool to rank a commercial and industrial site's ability to host electric vehicle charging stations as a distributed energy resource. And what the ultimate goal was to come up with a spreadsheet that ranks the predetermined sites that DER NetSoft gave us and rank them based on a series of categories and subcategories that we were determined would be optimal for comparing the sites against each other. The ultimate purpose of this Excel spreadsheet ranking tool is so that DER NetSoft can establish a methodology for scaling up this ranking scheme for distributed energy resources using a kind of mock city of San Leandro, as I previously mentioned, but to scale it up to other cities and localities across the country. And what their goal is to build kind of an AI neural network that can determine which sites are ideal for DER hosting of different assets. So the asset we were focused on was electric vehicles for this year. What they're looking for is kind of to determine which sites can be most feasible and then approach cities, the sites themselves, DER vendors into applying and building these distributed energy resources, maximizing the full energy potential of the commercial and industrial sites.
So, like we said, to break down some of these terms, a lot of you have experience in the industry, but if it's not clear, let's just, put this out there. Distributed energy resources, DER, what we mean by that is small energy generators, generally in the range of under 50 megawatts. And the difference here is that these are decentralized resources. They're not under the umbrella of a utility that's controlling, planning for them, and operating them. So on this chart here, you see on the left side and connected by the gray lines, you've got a traditional grid century plan like it has been for many, many years. But, the up and coming changes in the utility landscape have introduced a lot of variability in the resources, more small distributed, decentralized resources, and that's what we're exploring. We're exploring the EVs in combination with solar, with storage, in what we're calling an advanced energy community. And what that is essentially rolling up these small units of power generation and load as well, managing them together and making decisions in a way that's optimal for that location's resources and that location's needs. And that's what DER NetSoft aims to do, is to be a data analytics provider, be a platform that aggregates all of that, gives you not only the intelligence you need to in terms of usage and how things are trending, but allow you to become more of a prosumer, as you call it, and as they call it, and eventually a market participator, like Eric was showing in that previous slide, really engaging the customer to allow them to benefit from the resources on site in a way that wasn't possible before.
So the driving force behind this Capstone project and also DER NetSoft's goal is to help communities adopt distributed energy resources so that they can reduce their greenhouse gas emissions. So in 2009, San Leandro, which is the pilot city, adopted a climate action plan, and their ultimate goal was to reduce greenhouse gas emissions by 80% below 2005 levels by 2050. So as you can see in this figure below, this is from the city's report, commercial energy and residential energy over the past 10 years have decreased. However, you can see that transportation sector emissions have increased in San Leandro. In fact, San Leandro, their transportation sector is responsible for 60% of the city's emissions. So one of the actions that San Leandro addresses in their climate plans is to adopt more charging stations and incentivize businesses in the city to do so. But as you can see, they still need some help with doing that. So if they did adopt more electric vehicles in San Leandro, that can help reduce their transportation emissions.
And as Emma pointed out, transportation emissions are a huge part of the city's overall GHG emissions. And with San Leandro, it's kind of interesting because it's a city that's in, sort of a highway, so it gets a lot of throughput traffic, but a large chunk of the city emissions does come from employee commutes. The city has about 50,000 employees, and 90% of the workforce is commuting into the city day in and day out, according to census data. And a lot of those people are driving alone. Some of them are carpooling. And as we know from our literature research, if you think about deploying charging stations, it's often linked with adoption of EVs. And in California, being a progressive state, they're ahead of the curve in terms of adoption. But something that's been identified is that the adoption of EVs is going to be a key piece of getting more people to jump on the bandwagon, reduce that range anxiety. And when you think about commuting, for the city of San Leandro, and this is data that's available for other places, on average, people are commuting about 35 miles for their commute. So we've identified that level 2 charging is the most appropriate for the workplace, getting within the range of miles they need for a few hours of charging during the workday. And if you think about it, you're at work for 8 hours, sometimes 12 or more. But, so we've identified that could be the solution that we target in this community.
So as Vinny was mentioning, electric vehicle adoption can help California meet their climate action plan goals. So former California Governor Brown actually signed an executive order to increase the number of zero emission vehicles in California to 5 million by 2030. So as Vinny was saying, in order to get to this number of electric vehicles, you need to adopt charging stations. So another part of this executive order was to increase the number of charging stations in California to about 250,000 by 2025. So just to add how important it is to have electric vehicle charging stations, it's been shown in a lot of studies that not just charging stations have a better chance of increasing in electric vehicle sales than addressing other barriers such as cost and income. And in fact, in one company of a case study that we were looking at, they installed 50 workplace charging stations, and then over half of their employees ended up buying and now drive electric vehicles to work.
Multiple studies have taken a look at this infrastructure need. So you've got more EVs on the road, people are adopting it more aggressively. What's that going to look like in terms of the charging stations? If you buy a car today, getting to a gas station is not really something that worries you. You can find those easily. Although I've been on the road before and haven't realized the gas was almost running out. So that gave me a little bit of range anxiety. So in this case, planning and thinking ahead will involve really taking a careful look at where will be the demand, and how do you meet that demand? Is it in fast charging stations along the highway? Is it in public spots? Is it in your workplace? A couple of the studies we looked at, and this modeling output in particular is from NREL's 2019 view of the county San Leandro's in, indicates that a large chunk of the public charging is going to be happening at work. A lot of data from other research supports this, because that is a place where people spend a lot of the daytime charging. And as Emma will talk in more detail, it's also time where there's an abundance of renewable resources on the grid. So, that overlap is really interesting. So what we see here is that, we're on the right track. We're looking at EV charging. We're looking at the workplaces at these commercial and industrial sites. And now we want to think about, how do you stack them up against each other? And Eric will jump in now to talk about some of the previous work to ground us on this year's work.
Hey, can you guys hear me? I lost you at the end, Vinny.
Oh yeah, I was just closing up there and saying that you'll jump in now to walk us through some of the previous work.
Thanks. So our project is a continuation of 2 years previous Capstone projects. So what DER NetSoft did was they determined 6 commercial and industrial sites that would be ideal for DER adoption. And the first year, they looked at installing rooftop solar and ranking rooftop solar as a DER asset on those sites. Last year, as a continuation of that project, they added energy storage. So they looked at rooftop solar and energy storage in combination to see how they ranked amongst the commercial and industrial sites. To get kind of the ideal sizing for rooftop and solar and for battery storage, they use this tool called Reop Lite, which determines the number of hours that the solar would be discharging, that the battery would be charging and discharging, and how that would work in tandem with the average facility load for the year. And we took this tool and we used it as well when we added electric vehicles as a load, and saw how kind of the rooftop solar and battery storage changed a little bit. What they did also was they came up with 4 categories to rank the rooftop solar and battery storage. And we ultimately decided to follow a similar route, but we combined and expanded on a few of these attributes. So the first ranking was operational. The next was financial and economic, and the third was the environmental benefit of installing these DERs at each site. And what they did was they ranked each category and determined which sites were ideal based on weights and weighting percentages on what value a consumer would want the most, whether they want to reduce their grid GHG emissions the most, or they want to look at the financial benefit of the asset and value that the most. And ultimately, the tool gives you a total ranking score based on what you're looking for as far as which attributes and categories are the most important to you.
So as a continuation from the previous projects, this year we're going to be looking at adding electric vehicles as an additional DER. So in order for us to incorporate electric vehicles into the DER rating index, we're going to walk through the rest of this presentation discussing our methodology using an example site, DER 52. So we ended up choosing this example site because at that actual site in San Leandro, there are already 4 publicly available charging stations. The other charging stations, we had to use more educated assumptions, but for DER 52, we were actually able to use some real information. So the very first step in the methodology that we used was to determine the electric vehicle load. So for DER 52, you can see that we got some pretty accurate estimates because there were 4 charging stations at that site. So after doing that, we were able to get the annual energy consumption at this site. With the EV load added, we were able to determine how many EV miles these 4 public charging stations were able to charge. And then we also determined the utilization rate of these charging stations using that EV load calculation. So then the next step that we'll talk about later is that we then inputted that electric vehicle load into the site load. So we added the 2 together to determine the optimal PV and battery storage size for that site. And then after that, we'll talk about the specific metrics that we calculated, the financial, sustainable, and operational metrics. And those metrics were used to help us develop an Excel tool to rank all of these sites' ability to host their personal DER resources.
Thanks. So as previously mentioned, the first step in our ranking or determining any sort of ranking methodology for electric vehicles was determining what the load was going to be. So we decided to do this in 2 different ways based on research into current charging behaviors for people with electric vehicles. So the first way we looked at it was employees who would be charging their electric vehicles at work. And the way we calculated the electric load here is based on the number of employees, the percentage of employees who drive to work in San Leandro, the percent of them who own EVs, and then we broke this down into 2 behavioral categories. There's a percentage of people who charge at home and work, and then there's a percentage of people who only charge at work, whereas the remainder would charge solely at home. And so we added those, we multiplied the percentages of each charging behavior by their average commute or miles driven in a day, and then the electric vehicle efficiency averaged for most electric vehicles currently on the road. And we use this to determine the load for this sample site, DER 52, for the employees who charge only at work, and then the employees who charge at work and home, what that load would be on a daily basis. The other thing we had to consider was for sites that had customers visiting. So what we did was we took the number of customers who would visit each site, we multiplied that by the percentages who had electric vehicles, and then there's also a percentage of customers who have EVs who actually decide to charge at a retail location, and then we multiplied that by the average time at a retail location and the charge speed of the level 2 chargers. And we were able to determine what the average customer charge would be as far as electric vehicles. And then we could add all 3 of those together to get the total site, employee, and customer charging load for a day. And then we calculated that out for the year as well.
So DER 52, the site that we're specifically looking at, is considered we call it a destination site. That means we're both considering both employees and customers charging at this site. So it'll use the total combination of the EV load calculations that Eric was just talking about. So the next step in the methodology, once we determine that EV load, is to determine the hourly load profile of that EV load, and then optimize it using the re-op system to determine the best PV and battery storage size. So as you can see in this graph right here, we determined that DER 52, since it had an 80% utilization rate, that means its 4 charging stations are going to be used 80% of the time during the day. So that was between 8 a.m. and 9 p.m. However, there's also a utilization. It depends on the hour. So when it's busier, the utilization rate for the hour will be higher. So typically when it's busier around 3 p.m. to 6 p.m. So then you'll see that right here, this green line, this EV load right here, plus the site load, you'll see that it increases there. So then the re-op simulation was then run again to determine the optimal site loads. So before you added this EV load, these were the best PV and battery system sizes. But after you added that additional load, these became the optimal PV and battery system sizes. So you can see it didn't increase that much, but it did increase a little bit. And you can see here that this PV serving the EV load, because you increased the size of these systems, the EV load was able to be charged by the PV solar systems.
So now we'll step through the methodology for some of the details under our 3 categories. And we'll start with operational, and Eric will walk us through that.
Financial. So I'm going to walk you through kind of the operational metrics that we determined. So the first thing we have to consider when installing any sort of DER or energy resource is, can the utility distribution or feeder lines handle the DER support additions? So the way we did this was by determining 2 different line ranking schemes. The first one is for load. Can the feeder line handle the additional load of the energy storage system to charge it?
I think we lost Eric there for a second.
Adoption and looking at ideal sites for implementations. So I was able to determine which feeder line was going into each site, and it gives you a load hosting capacity and a PV hosting capacity that is currently rated for the line. So we were able to rank what the ideal sizes were given from re-opt and compare them to these limits. And what we found was that 25% of the sites can actually not support PV without feeder line upgrades, and 7% cannot support any sort of energy storage and additional EV load without any sort of feeder line upgrades. The other thing we had to consider was the DER impact on energy consumption. So obviously, PV generation and energy storage generation will help a site use less energy from the grid, but it's also going to take a little bit more energy charging the battery and charging your electric vehicles. So we had to subtract those from the impact on energy consumption. We also had to compare it to the total feeder line. So we looked at the total energy consumption across the feeder line that was contained all those DER sites. And then we ranked what that site's impact on the total feeder line energy consumption was. So what we found is not all sites see energy consumption reduction. There was a few that had solar and storage sites that had that were really small in terms of capacity. So they actually consumed a little bit more energy on an annual basis. But another interesting thing to consider is, while sites look like they have a huge annual energy reduction, they only have a small impact on the total feeder line energy reduction percentage. I also looked at it as far as a peak shavings reduction benefit. So of the feeder line's peak load, how much is reduced because of the PV and energy storage with the additional EV load? And so I ranked this 2 different ways. One was how much peak load was reduced by the DERs, and the other was, again, looking at the line as a whole, seeing what percentage of the line's total peak load reduction each site had contributed. And what we found for this is all sites do experience some peak load reduction, but the impact is obviously different in some versus the others. You could I wanted to consider was, how do DERs respond in a grid outage event? So the facility resiliency is what percentage of the facility's average load can the DER support? The battery's capacity duration. You go to the next slide, Emma.
Eric, this one?
Yep. And so the overall DER grid benefits are, we have to determine what what DERs can do in terms of resiliency. Can they supply power to the grid? Load, can they supply power or charge from the grid? And then voltage, this was another metric that I was slightly considering, but we didn't have a full chance to adopt because a lot of the charging stations were kind of the same size. So that will be looked at further. Was what benefit can charging do by changing the charging rates or patterns as far as, grid voltage support? And this is the final overall ranking scale for all the operational metrics that were each ranking category was weighted and normalized, and then the overall operational metrics were used to determine which site would be ideal for DER installation based on the metrics that I calculated. The solid blue line is DER 52, which is relatively high on the ranking scale as far as operational metrics, but it will look a little bit differently when we get to the overall final ranking scheme at the end.
So my task was to identify metrics to quantify the sustainability benefits of adopting distributed energy resources at each site. So this is a look at the definition of sustainability. So sustainable development should address multiple issues: economic prosperity, social equity, and environmental stewardship. And electric vehicles actually do a really good job at addressing not just the environmental stewardship aspect, but the other aspects of sustainability. So US energy security and reducing electricity rates will address economic prosperity due to cost savings and profit. Decreasing city smog will address health issues. And of course, increasing renewable energy and decreasing emissions will address environmental stewardship. So these metrics right here will quantify sustainable benefits for the city to use. So the increase in city tax revenue metric focuses on the ability of electric vehicles to reduce communities' dependence on oil, thus boosting their economy. The healthcare metric focuses on the fact that EVs no longer emit tailpipe emissions, and these tailpipe emissions have particulates in them which can damage a person's respiratory health. The number of trees preserved calculation discusses how a distributed energy resource on top of a CNI site, now that it's a rooftop, is using land that is already used. So you'll save land by not doing that, instead of choosing to clear land to put a utility scale solar system in. The water consumption reduction metric is a result of replacing your facility load with PV solar, having it dependent on PV solar instead of the grid. Because the grid, when you're consuming energy, that grid is also consuming, the plants that power the grids are consuming a lot of water to cool their plants down. So the largest and the most important metric that we looked at was the greenhouse gas emission reduction of electric vehicle adoption. So this metric first considers the avoided tailpipe emissions that electric vehicles no longer are releasing. And a charging station is what enables an electric vehicle to do this. However, the electric vehicle charging station has to get its power from somewhere, and this is from the grid. So the first step of this is in the calculation is that it assumes that all of the EV miles that need to be charged are charged by the grid. However, if you put a PV solar system or battery storage system on your site that is able to account for this additional EV load, you might see that the greenhouse gas emission reduction is actually gains some emission reductions because now the PV is charging the site. So I just looked here at DER 52. You can see that it avoids a maximum amount of 567 emissions, but because the PV and battery completely charge all of the EV emissions for that site on this particular day, it reaches its maximum amount of a GHG emission reductions, which is 567. So some other things that can impact, so if your vehicle does have to charge by the grid, that grid emission rate is dependent on a lot of factors, including the regional grid generation mix. So as you can see in California, the regional grid generation mix means that has a lot more renewable energy on it. So an all-electric vehicle will not produce as many annual emissions as if you charged a similar electric vehicle with that same amount of load on a different regional grid that is, say, similar to the grid generation mix of the national averages. Another factor that impacts GHG emission rates of the grid is the time that you're choosing to charge or get load from the grid. So as you can see, this is from California, the grid emission rate changes every single hour. So it's the lowest during the daytime. So if you align your workplace charging with that daytime, then your emissions will be lower if you have to charge your electric vehicles at the workplace from the grid. So this is just another benefit of workplace charging. So this shows some of the data that we used using the DER sites that we had to really show the different charging scenarios, depending on what time you charge, their ability to reduce emissions. So you can see here some workplace charging sites. They were able to, so if they're charged during the daytime, they're able to result in a higher GHG emission reduction. If you choose to charge in the evening time, there's going to be an 11% decrease in emission reduction potential. If you charge that exact same EV load, but instead charge it at night, there's going to be a 12% decrease in emission reduction potential. So this applies to workplace sites, but even destination sites that charge electric vehicles both during the daytime and a little bit into the evening, there will be a 9% decrease in emission reduction potential if you choose to charge that electric vehicle at night instead. So now we'll move on to the financial metrics with Vinny.
Thanks, Emma. So the way we were thinking about this, the financial metrics is, as with any project, any investment, the owners of the sites would want to know, is this, a net positive to me, or is it just going to be additional costs or something I have to invest? The way we went about creating that is looking at any revenue generating opportunities, taking into account all costs, including both initial costs and ongoing operating costs, to build a site-specific discounted cash flow model to bring a 10-year view of this project, the economics of running a charging station or 10 of them at a site, to see what that looks like. So we looked at annual profits from charging station, considering how you can make money out of it and what costs to you are there. We built in the ability to put in subsidies and rebates. At the moment, some of the opportunities for the San Leandro areas in the county there weren't any programs we could put in, but we built in that functionality for the future. And then we looked at some of the metrics on equipment and installation costs for the EV project. So starting with the revenue, what we wanted to consider is, how can an electric station or charging station make money? Three key ways that happens is, first, through electric sales, the actual charging. Second, grid services. So, any way you connect with the utility and benefit that way. And lastly, on advertising. So in terms of considering it for our ratings, electric sales were the only ones that we included. Grid services are an emerging area for this. San Francisco has some programs that are fully subscribed, so we couldn't really model out anything in that way to show what the benefit was, but there are potential benefits there. So if we double click on electric sales, there are three distinct revenue models that are already taking place in San Leandro. So the Department of Energy has a database of all charging stations across the country for electric vehicles. We looked at level 2 charging stations in the city, And you can notice out of the 56 charging stations there, for the ones that do charge, they either charge on an energy plus session fee model, an hourly rate model, so sort of, park and pay for the hour, and lastly, an energy rate, which is pretty much a markup on, what they buy the electricity for and what they sell it to you. So that sort of covers some of our assumptions on the revenue side. We made the tool be flexible so the site owner can choose. I'm choosing between some of these models. I get to play around and see what that looks like. If we go on to the next slide on costs, we built a view of both the cost to install, so the capital costs, and the operating costs of running this. So on the capital side, main thing there is the labor of putting it together, and second, the materials. On the operating side, looking at both electric and non-electric costs. So on the electric side, you've got the energy and demand charges for your energy bill, and on the non-electric, maintenance and repairs, networking fees if you're plugged into a network of EV charging stations. That kind of gives the full picture of a specific project economics. Now, we looked at DR 52 because we had some view of how many stations were there and a better visibility into the load. So taking a look at that and the assumptions built into our tool, you see that energy only is the clear winner here in terms of revenue, almost making $60,000 a year. And over a 10-year period, it generates about $188,000 in net present value. So that's taken into account, over the 10-year life, let's say, of this charging station we're considering. That's how much value it generates to the owner. One thing to note is that what we were looking at is, as a consumer of the charging station, you can charge at home if you have a charger, plug into the wall, or you could go to these sites and pay for the use. At this rate, at the 60 cent per kilowatt hour rate, it's almost a 3x markup on what you pay for at home. So deploying this will really mean, people are willing to pay for the convenience. And so far in San Leandro, it looks like, charging stations have been charging this much. So it'll be up to sites to determine, if I'm charging this to my employee, where do I want to put this? And that will really determine how profitable you can be, how much of your operating costs, capital costs you're covering for that, on a site-by-site basis. Again, ultimately what we aim to do is hand this over to DRNetSoft so that they can run this on every site they interact with and give those customers a range of possibilities and a range of results they can consider. So if we go on to the next slide, Eric will walk you through how this all comes together in the tool that we put together for them.
So going through all of our metrics, what we did was we normalized each category and then subcategory ranking. So each site is ranked in terms of the operational subcategories and then the financial and sustainability metrics. From there, those were given an overall rating score, and you can play around with the weightings on the top part of the sheet. So if you value one subcategory or category over another, you can determine which ratings or you want to put the most emphasis on. From there, it gives you a ranking of what each site is overall, using kind of the weights that you've given it. And then it gives a final ranking and then a final percentile ranking at the end of all the 68 commercial and industrial sites. So this was our final ranking scheme for all the sites. Obviously, DER 52 ranked well and above all of the other ones. And the main reason is we actually had some real data to use and implement in our methodology. So we were able to determine kind of what the actual number of employees and customers would be. And we actually knew how many charging stations would be at the site. So we could come up with a good numbers in terms of what the charging energy consumption would be and the financial and sustainability benefits of it. Overall, this is a very high scale or high level tool, and what it's designed to do is look for not just San Leandro, but for communities across the country, so that the variables can be changed. And our methodology requires a lot of known information as far as employee numbers and who's actually driving. So we used really educated assumptions to determine what we thought the employee headcount would be at each site and how many people would actually be charging, to determine what the number of charging stations would be and what the energy consumption would be at each site. But these were just assumptions that we made, and we didn't have a real number for what the total EV charging would look like at each site, which is why this was kind of skewed one way towards the one site that we did have information for.
And like Eric pointed out, one of the key pieces here is going to be getting at that real data. So a lot of the literature on charging for the workplace involves first an understanding, a situational awareness of, what is going to be the demand here, and what is the evolution of that in terms of my employees, my customers, who drives EVs, and what is that behavior going to look like. So collecting that site real data will be a first step in terms of future work and building out more results out of this, and updating those modeling assumptions to ultimately run the simulation of advanced energy communities. So you've got all the intelligence together, and then you can look at the whole community as a whole and see how you can optimize. And like Eric pointed out earlier, using those AI tools that DER NetSoft has been trying to develop, how can you make informed assumptions based on all this knowledge you have on the community's consumption and generation from all these different resources. So ultimately, the aim is to integrate this rating, the solar and battery storage rating, into the DER NetSoft current offering, which sort of looks like a dashboard online that customers have access to, and they work on a subscription model, different types of offerings out there. So what they hope to do is build on from the methodology, the work we've done here, and implement that into their interface, and present this to their customers as an additional tool that they can have in terms of managing, strategizing around their energy use, and ultimately making sure they're monetizing as much as they can out of either owning solar panels, battery storage, and EV charging stations. So this concludes our presentation, and I know we've been talking for a while, so let's see if you have any questions.
All right, thank you, team one. Questions? You can either ask it verbally, or you can send me a question through chat, or all of the above. Question for team one.
Rudy, I have one.
Yes, Cheryl, please, go ahead.
Great job, especially under the current circumstances, team one. My question is, are there plans for the model in the future, recognizing things are still being developed, to look at the financials when the charging stations are not being used to their fullest extent? And again, correct me if I'm wrong, it looked like your model is looking at the maximum utilization of those charging stations, which of course allows that site to be, in essence, kind of adding an adder to that, to supplying that service, but that would imply that they're being used to their fullest extent. So does the model account for a minimum usage, and when kind of the economics might start to fall apart?
Yeah, that's a great question. So we did build in the ability to put in a utilization rate, so that your site, if you know that, we could potentially be charging 10 hours a day, but honestly, really 30% of the time is being used, that could be reflected. Another way to think about it too is building in a calculation on what does it take to break even? So we put that in place too, so you could see, okay, well, this is at the point where we, really on a volumetric, or even like how you charge on the rate, what that could look like. So that's something we considered, but again, we don't really have real data to really ascertain for sure what the numbers are, but that's something we thought about, because oftentimes these charging stations are just sitting there, especially if there's not, enough demand or adoption in a specific city.
Thank you.
I guess from an energy use standpoint, we kind of put some slack in too, whereas when we determine, people charging for like 0.217 of an hour, we kind of said they were there charging for 3 hours, because not, employees don't always have the luxury of just running out and moving a vehicle around every 5 minutes when they, when they're done charging. So there is some slack in terms of the energy consumption, as, adjusting for some behaviors, as, people can't always respond to, the second their car is done charging.
Thank you.
Anything else for the team, for team one? While you're still thinking of questions, just want to point out Emma is our first undergraduate student to work on a Capstone project with her peers who are in the MNG program. And so thank you, Emma. I think it was the dean's dream to have this kind of collaboration, and she'll be going to an internship over the summer, God willing, that things are open. And Eric is going to go on for an MBA degree at Lehigh after he finishes here. And Vinny is going to Boston Consulting Group in Boston. Congratulations, guys, on your next steps. We do have time for 1 or 2 questions for the team. All right, so Emma, if you can disengage, unshare your screen and have team 2, Nicholas, get on, Nicholas Vinansky. Thank you, team 1.
Thank you, Rudy.
Thank you.
All right, Nick.
All right, can everybody hear me?
Yes, we can hear you.
All right, just let me share my screen.
And as Nick is setting up, he had a project with PP&L, and his project manager is in the audience. Alad, thank you very much.
All right, before I begin, I just want to thank everyone for being here today and listening to these presentations. And of course, I want to thank my project sponsor, Hala Scala, for all his help with this project. With that being said, I'm Nick Vinansky, and today I'll be presenting to you the topic of my capstone research, which is entitled Volt-VAR Control, Impact and Benefit Analysis. To begin, I'd like to present a brief outline of what I'll be discussing today. So I will be starting with background on the project, exactly what Volt-VAR control is, and why I'm doing this analysis. Secondly, I will provide a first semester recap of everything I completed the first semester and how it applies to LVM, savings, and things of that nature. Additionally, I will go into my second semester goals. So what my goals were for the semester include an examination of bellwether data, which is downstream meter data and its impact on LVM plan generation process. And additionally, I would perform a financial analysis on the LVM generation system based on customer rates. From here, I'm going to move into the methodology I used to complete these goals, the results obtained, and the conclusions drawn from the results I obtained. So to begin, my project is sponsored by PPL, specifically by their distribution operations team. And my goal is to perform an impact and benefit analysis of the Volt-VAR control software. So essentially, my goal is to determine how PPL is benefiting operationally as well as financially from the use of this Volt-VAR control software. But the software that they use is called Load and Volt-VAR Management, or LVM. And the way that this process works is that SCADA measurements from feeder lines are used to correct power factor and provide voltage regulation throughout the distribution network. Additionally, this is done through the use of 3 major devices, which are capacitor banks, voltage regulators, and load tap change transformers. Now I'll get into the first semester recap, so everything I completed the first semester. In the first semester, I examined upstream voltages, specifically at the bus level. So I looked at bus voltages at 3 different substations, and using a year's worth of data, I created average bus voltage curves over a 24-hour period. And from here, I calculated the standard deviation in each of the bus curves and determined that the substations that were utilizing LVM for the entirety of the year experienced a much lower standard deviation, as well as a much flatter voltage curve as shown here. And this was indicative that the LVM application was working as intended. So as shown by the results on the right-hand side over here, we see that station 3, which operated under LVM for the whole year, had a standard deviation of 0.03 in the bus curve, as shown here. Station 2, which operated for a portion of the year under LVM, had a standard deviation of 0.07, also very low. And then Station 2 for the months of July and August did not utilize LVM and experienced much higher standard deviations. From here, I'm going to discuss my goals for this semester. So what I wanted to look at was examining bellwether data and its impact on LVM plan generation. So bellwether data is essentially a different algorithm than the LVM algorithm that's used. LVM has the possibility to be paired with AMI, or automated meter infrastructure. And what's done is the bellwether algorithm determines the 5 highest voltages and 5 lowest voltages on the feeders coming from the substation. So that's 10 total points. And then ideally, the LVM algorithm runs 20 seconds after this process occurs and determines exactly which points to consider in its LVM plan generation process. Additionally, I performed a financial analysis of the LVM application from the customer perspective, which resulted in some pretty great results in the hundreds of thousands of dollars. So the methodology used for the first portion of this project, I examined 24 hours worth of data from a Harrisburg substation. Data was collected every 30 minutes over a 24-hour period, meaning I had 48 bellwether files to examine and 48 LVM files to examine. From here, I compared the bellwether recorded data with the LVM plan generation data, and then determined the LVM plan dependence on bellwether data. This is shown in the next slide. So essentially what I did was I used the bellwether files that were accepted. So of the 48 total files, only 25 of the LVM plans were actually accepted. An LVM plan can either be accepted or rejected in the LVM plan validation phase. The plan will be rejected if power factor is not corrected or if there's still voltage problems within the system. So of the 25 accepted LVM plans, I determined that 98% of the time, the bellwether data was considered in the LVM plan generation process. And the way I did this was I matched the load IDs and meter IDs shown here. So this is an example of what the bellwether data would look like. So these are the 5 highest voltages that were recorded on the line for feeder 1, and these are the 5 lowest voltages, which were from feeder 2. From here, I compared the load IDs and meter IDs here with the LVM plan generation and saw that it matched 98% of the time as shown. This 2% that was not matched could be contributed to the system design. So it was originally thought that bellwether data was not really considered in the LVM plan generation process. So it will not necessarily be used all the time in LVM plan generation. From here, I'm going to move on to the methodology used for the financial analysis portion of the project. So I was provided data for the same substation that I was referring to for the date of January 30th, 2020, and the date of March 27th, 2020. The January data was data that involved the LVM process, and the March data did not involve the LVM process. So what I wanted to determine exactly was how the voltage between the 2 days changed over the course of that time period. So what I did was calculate the total instantaneous voltage on each feeder by summing all of the meter readings on the feeder for both of the days. And then I took the difference between the two different days to determine the total voltage difference between the two. From here, I calculated total line impedance and transformer impedance based on specific assumptions that I will get into on the next slide. And then I calculated current using total voltage and impedance. So I took the total voltage from the first step and divided by the total impedance to get total current values for both of the days. I then took the difference in the current for both of the days to calculate the change in power between the two specific days. And this was done by multiplying the change in current by the change in voltage. From here, I converted to megawatt hours over a 24-hour period, and then I multiplied by a customer rate of $7.49 per kilowatt hour to obtain financial result. So the assumptions used in these calculations include a feeder length of 10 miles, which was an arbitrary value, a wire material of number 4 copper, the fact that line impedance was based on the wire material determined, and that transformer impedance used was the PPL specified minimum value. So these are the results of the voltage portion that I discussed. As you can see, this is during LVM, this was not during LVM. And these are the change in voltage between the 2 days. So as you see, the voltage on feeder 1 increased by 1,078 volts, feeder 2 increased by 321 volts, and feeder 3 increased by 1,800 volts. Based solely on line impedance, I calculated financial savings for the year for the customers on the line to be $174,000 for feeder 1, $15,000 for feeder 2, and $486,000 for feeder 3. I performed additional calculations as well. This calculation was based solely on transformer impedance, not considering line impedance at all. Using these assumptions, I determined that the financial savings for feeder 1 were $70,000, feeder 2 was $7,000, and feeder 3 was $195,000. Finally, I did one final calculation based on both total transformer impedance and total line impedance and determined financial savings of $50,000, $4,000, and $139,000. So based on these results that we obtained, we saw that the voltage increased along each feeder while not under LVM operation. Feeder 3 experienced the greatest change in voltage and thus the greatest financial savings. And the financial savings ranged from thousands of dollars to hundreds of thousands of dollars in each case, no matter the assumptions. In conclusion, the bellwether data is considered heavily in the LVM plan generation process, as shown previously. The voltage along feeders is lower under LVM operation, which was shown in the first semester results, as well as the financial results. The customer does in fact benefit financially from the use of LVM in the units of thousands to hundreds of thousands of dollars. And finally, PPL benefits operationally from LVM as voltage is lower along distribution lines, leading to a longer system life. And with that, I'm going to open up the floor to questions. Thank you.
Thank you, Nick. Questions for Nick Vinansky?
Rudy, can you hear me okay?
Please speak up.
Rudy, it's Al Rutz. Can you hear me?
Yes, yes, we can hear you. Go ahead, Al.
Nick, couple of questions. I just joined halfway through your presentation. My
Yes.
apologies, but I saw a couple of the assumptions there that I think are pretty far off from reality.
Okay.
It said that you assumed number 4 copper on the lines.
Yeah.
And a line like that leaving a major substation would be far greater than that. It'd probably be 477 or 336 aluminum.
Okay.
And the lines out of that Harrisburg substation are nowhere near 10 miles long. So I just was curious, how much would those data points, how much would those assumptions be skewed if let's say if the feeder was only 5 miles long and the wire size was 5 or 10 times the circular mill of what the assumptions were?
Well, we would get much different results, definitely much less financial savings. Wait, no, actually, excuse me. We would have greater financial savings in that case because the model was specifically based on line impedance. So with less impedance, you would have greater currents. And based on the model that I used, that would result in greater power change and thus greater financial savings. Does that make sense?
Yeah, I think so. Yeah, I said it was like, I'm not sure. Did they not give you actual feeder sizes and lengths? That you had to make those kind of assumptions?
The assumptions were made with the help of my project sponsor. So that's how I came up with those assumptions. I didn't necessarily come up with those on my own. We decided that that was the best idea to do.
Okay, and these are all overhead circuits, I'm assuming.
Yes, as far as I know.
Okay, all right, thanks, Nick.
Any other questions for Nick?
Hi, Nick. This is Kim Gautner from PPL. I wasn't your sponsor on this project. My colleagues were, but I very much enjoyed it. To Al's point, the average feeder at PPL is actually 27 miles long. Out of the 1,200 circuits that we have, our average is 27 miles long. So how would that affect the financial calculation?
Well, with the longer the feeder, the greater line impedance that you would have, which would result in a lower current, which would definitely result in lower financial savings. Does that make sense?
Would it be proportional?
Based on the model that I used, I don't believe so. Because, well, actually, yes, it might be proportional because then we would have larger voltage on the line as well. Right?
Your voltage at the bus would remain the same at the substation or similar, but it's an interesting thought process. The other challenge with a really long line, a line as long as 27 miles, some of our lines are as long as 100 miles, that voltage is harder to control as a whole. So that's one of the benefits PPL is at least thinking that LVM might be able to provide is better control on these very long, stringy feeders that the rural areas of Pennsylvania are notorious for. So I think that might be a slightly different calculation, but still this is still very valuable data and a really solid calculation. So thank you.
Thank you.
Yeah, this is Al again. Kim, when you say a feeder is 27 miles, you have to be assuming like the additive length of each individual single phase, three phase, whatever. Whereas when I look at the length of a line, it's like maybe the longest continuous, not the sum of all the little feeders going off to the side. When you say 27 miles, you're saying there's 27 miles of conductor on the line, I hope, and not that there's 27 miles from the start to the most distant point.
Right, that's 27 line miles. So that's single phase and three phase combined. It's not each conductor on three phase added together, but it is a three phase line versus a single phase line. Typically, it is not 27 miles from substation to the last customer on the line, or the farthest customer on the line. That's a good point.
Yeah. Again, I haven't seen Nick's total model, but you can't assume that all that current flows all that distance for 27 miles, for instance.
Right, absolutely.
Okay, thanks.
Anything else for Vinny? Nick, sorry. All right, thank you, Nick. So why don't you unhook your screen and have team 3, which is Stanley, I believe.
Good afternoon, everyone. Let's figure out how to share. Okay, here we are. Good afternoon. My name is Stanley Worthington. I am excited to talk to you all today about my project. And you may notice that I am wearing a shirt which follows in the theme of my research, pumped hydro in Hawaii. So I thought that a Hawaiian shirt would drive the point home. So pumped hydro, I'd like to start with a quick explanation of what we're talking about today. So utilizing energy transfers, the potential energy stored in the water at the upper reservoir, changes into mechanical energy, spins a generator, produces electrical energy. So you might look at that and say, okay, great, yep, it's a huge battery. And that's exactly what it is. And it actually has a surprisingly good efficiency. Most installed pumped hydro throughout the industry is 70 to 80% efficient. But with that in mind, it is a net consumer of electricity. And to give you a little perspective on that pipe that is shown in the diagram going up and down, what that might look like in one example nearby Lehigh at Yards Creek, that's an 18-foot diameter pipe, and it's transferring water at elevation change of about 700 feet. So what you have, the energy you have to work with in the generation in that example is water in an 18-foot pipe that's actually traveling almost 25 miles an hour. It's an exciting amount of energy. So let's take the discussion to Hawaii. The energy situation in Hawaii is very unique because it's an island. And given that it is an island and it has limited resources, self-contained, it has a very aggressive renewable energy goal. They're looking at 100% by 2045. And they are an island. So unlike California or New York, if they get the math wrong, they can't just buy dirty power from Montana or Pennsylvania. They actually have to figure it out. And so let's go to Pearl Harbor. Since I'm a naval officer, my research involves the Department of Defense assets at the famous Pearl Harbor. Hawaii is an island, and it's a tropical island. And so as solar energy became more affordable, the installed solar PV in Hawaii has increased dramatically, and their duck curve is considerable, as you might imagine. And in fact, they have an intermediate goal of getting to 40% renewables by 2030. And as of 2017, they had 913 gigawatts installed. That's 9% of the statewide electricity is coming from solar PV, but only 1% of that is actually grid scale. The rest of it's behind the meter on homes. And so it's really quite a unique situation. Just this past year on Oahu's North Shore, a grid scale project went in at 49 megawatts. And that was a milestone for the island, certainly. However, if you think about the other 91% of the energy in Hawaii, it comes from fossil fuels and coal that are shipped in across the Pacific Ocean. So what that results in is a pretty bleak kilowatt per kilowatt hour price. It's almost 3 times what you would expect to pay in the States. And that is really what makes my project proposing pumped hydro in the state of Hawaii so unique. So what do we really talk? Well, before we get into that, Pearl Harbor's infrastructure that makes the pumped hydro possible. The Navy has a power purchase agreement with the utility at 12 cents per kilowatt hour. So the military pays almost like a continental United States energy rate because they allowed the utility to install this 11 megawatt solar farm right there on Pearl Harbor. So what you're looking at there on the right side of that solar array is Pearl Harbor itself. So what I'm proposing that the Navy does is take the energy from that solar farm and take it a very short distance across Pearl Harbor and put in a pumping station and pump seawater up into these tanks. Now, what are we looking at? These tanks, it's a very unique resource that the military has in Hawaii. It's 20 underground fuel storage tanks buried in a mountain up above Pearl Harbor. Each tank is colossal, 12.5 million gallons. And I have the Statue of Liberty there for size comparison without her base. Without her base, the Statue of Liberty could literally just rattle around inside of one of these tanks. That's how gigantic they are. And even with her base, you could wedge the statue into there. They're that big. And so total, we're looking at 250 million gallons of storage. Now this storage is being actively used. So the Navy indicated that at most they would allow 2 of the tanks to be converted to pumped hydro, and they would give me the space in this tunnel to put 2 32-inch pipes. So that's what we're looking at. And to summarize our question up to this point, can we take solar plus some tanks and a Francis turbine, and is that the same as having diesel and a generator, which is essentially Hawaii's alternative? So let's look at our parameters. One really unfortunate restriction is at the base of each of those tanks, buried in an unnegotiable amount of concrete, is a single 32-inch outlet at the base of each tank. And so that really limits the amount of flow rate you can get out of the tank. And another kind of bleak statistic here, or data here, is that it's a shallow gradient. It's very much not what you would traditionally look for in a pumped hydro scenario. We're looking at a 1% gradient over 2.5 miles. At Yards Creek, they might have it's like a 40 or 35% gradient, and it was like at most 1/8 of a mile away. Very, very different. And in addition, those space considerations that I mentioned. So what you come up with, we'll talk about this with respect to storage capacity in megawatt hours and the power capacity in megawatts. And so your megawatt hours, if you take advantage of both of those tanks, you're getting 37.4 megawatt hours. And really the area under the curve represents the total amount of energy stored. And so your megawatts is kind of the more key aspect here with respect to the military. If you look at that graph, you'll notice that as the free surface of that tank decreases, you lose the energy and you lose the flow rate, and you're not going to be able to spin that turbine as fast. And so what you get is a decrease over your 5 days of capacity from 3 megawatts down to 1 megawatt. So really what you can only count on is that 1 megawatt. And so if you flatline that back, what you're really looking at is the opportunity to do a pump back, a simultaneous pump back to take into account that area between the black dotted line and the blue line. And that has the opportunity to push you out further than 5 days. So the cost to pump seems pretty reasonable. The solar land lease agreement allows you to purchase energy fairly cheap, not great. And you can pump using the existing pump data from the Navy at 28,000 gallons per minute. It'll cost you $2,000 to charge one tank. And then that saves you, the CO2 savings from that is about eight and change tons of CO2. However, looking into that a little bit closer, it's going to cost you $69 million to do this project. So it's not optimistic from a financial perspective. If you were to just buy diesel fuel in a generator with that $69 million, you could have 57 years worth of fuel. So the trade-off for using this tank farm for flattening Hawaii's curve is, as I've determined, not really the most favorable plan. However, all hope is not lost. The DoD actually, as I dug into this a little deeper, is taking an active role in helping Hawaii reach that energy goal with the Kauai Island Solar and Storage Project. And so what this is the Missile Defense Agency, again, with a power purchase agreement, has constructed 19 megawatts of solar PV paired with an on-site 70 megawatt hour Tesla battery. This is really an exciting project, and it's just one island over from Oahu on the island of Kauai, which coincidentally is also the location of Mark Zuckerberg's 700-acre estate, a shining and tragic example of neo-colonialism. If you're bored, look it up. But what this really is it's hope that these projects of solar plus storage, partnerships with the Department of Defense and energy companies in Hawaii actually is a viable solution, albeit perhaps not with the conversion of the Red Hill bulk storage fuel facility. And finally, I'd like to end on a bright note. Arguably, the world's foremost supplier of coal energy pollution, China, is 100% on board the pumped hydro train. So looking at pumped hydro plants at 1,000 megawatts or greater, there's 69 of them in the world right now. China's got twice as many as we do. But the really cool thing is that right now, China burns 5 times more coal than its nearest country on the list. But in the near future, they're going to have 30 pumped hydro plants online, each one greater than 1,000 megawatts. So it's really optimistic for the future. Finally, I'd like to thank my many advisors and mentors from this project and from the Lehigh ESE program. It's been a very rewarding experience for me. And finally, I will open the floor to questions. I do apologize. I was not able to land precisely on the 10-minute mark like my colleague Nick. So I'll go ahead and stop the share so that people can see all of our smiling faces simultaneously. Any questions? And the question that perhaps is on everyone's mind is that, yes, I am the same uniformed military officer that was featured in the photograph. that Rudy showed earlier. It's true.
Questions
Jim,
for, yes, James?
yes, just one question. As you were going through your presentation, I was wondering about the economics of battery storage versus the pump storage, and in particular also versus the economics of battery storage against the diesel. We just did a project over the last year and a half down in Puerto Rico, and we found that behind the meter battery storage and even utility scale battery storage was a much more attractive option than the diesel generators. I'm wondering if you looked at that, if you did that economic analysis. And I have one other point after that.
I personally did not do an analysis on behind the meter battery storage. However, in Scott Thomas's 402 class, the other class the cohort has this semester, one of the other members of the class did look into that, and he actually found that the utility scale batteries were more financially viable than the behind the meter. So ahead of the meter was more viable. And he presented an interesting case, which you might be aware of from your work in Puerto Rico, a utility scale battery installation down in Australia that purports to be paying itself off at an alarming rate.
And that's a good point. Yeah, and that Australia project is worth looking at. Just the other point, you made a comment, the future is pump storage. That makes me wince a little bit. It made the dog get excited and everything. But when I see, historically, some of the environmental impacts of pump storage, that has to be factored into the equation. And, in many places around the country, pump storage projects have had a really serious environmental impact. So just with that being said, I don't know what the 30 projects under construction in China look like, but I would put a red flag up on that, say let's learn more about those projects.
Thank you. Actually, that is an outstanding point that I hadn't considered. I lived near the Olympic Peninsula for a while the National Park Service was decommissioning a dam out in Olympic National Park. And to see the environmental devastation caused by the Elwha Dam was really tragic. And I think that it would surprise me if the Chinese government did an adequate environmental impact assessment prior to citing those 30 plants. That's an excellent point.
Okay, thanks.
Okay, thank you, Stanley. Thank you for all the questions asked. So if you can unshare, and we'll get team 4 queued up. As they are queuing up, Stanley is going to Fort Eustis, is that correct? Under a joint integrated command. It's not a coastal area, so it's not Hawaii, it's in Virginia. So
yes,
Stanley.
I'm very excited. I'm going to be in a joint task force working for NORAD. And the signature block of the incumbent in that position says COVID-19 response, JTF Civil Squadron. So I don't know what that means, but I'm really excited to find out.
Okay. Thank you, Stanley. All right, team 4. You guys ready to roll?
Yep, we are ready.
All right, then go ahead.
Everyone can see?
All right, so my name is Nick Wagner. I'll have my teammate Josh introduce himself so you hear his voice as well.
Hello, everybody.
And today we will be talking to you about our project. We worked with PPL, and we were working on a technology and economic assessment of solar penetration in the PPL service territory. So just to walk you real quick through the outline of our presentation here, we're going to start with an introduction, during which we will each briefly go through the posters that we created for the midway point of this project back in December. Some of you may have been at that symposium and seen this already, but we want to make sure that we kind of lay the groundwork so everyone understands what we're talking about with community solar and with hosting capacity. Then after that, we'll jump in. We'll look at the ways that we mapped the hosting capacity. We'll follow up by looking at the ways that we mapped the other factors that relate to favorability of hosting capacity. Josh will talk about some of the costs associated with it, with building out these community solar farms. We will present our final composite favorability map, and then we'll talk about a couple other possibilities with it: rooftop potential, social equity, and some future work.
All right, so we're gonna dive right into it. So this is my poster from last semester, and we'll be looking at Nick's kind of two halves to the same picture. So the first part is just why on earth we're doing this. So this actually is tracking a House bill that's going through the state Senate right now in Pennsylvania. So it's House Bill 531, and it pretty much just works on getting community solar inside Pennsylvania and getting it approved. This is going to allow for a range up to 3 megawatts in Pennsylvania. So there's a lot of other states in the United States right now that allow for community solar. Pennsylvania is a little behind that right now. And this is going to be looking into the solar penetration within the PP&L service territory. So we're pretty much just going to be getting into a good reach inside of like the PP&L service territory. A lot of our data is collected directly from PP&L. And how this is going to affect the infrastructure if community solar does move into this area. Is there going to be an update that needs to be done? Or is it something that it can even be planned around so well by the developers that no infrastructure will need to be updated because of this?
So then moving on to my poster from last semester, I want to real quickly walk everyone through hosting capacity, just so they understand what that term is when we throw it around later in the presentation. Hosting capacity is the amount of distributed energy generation that can be added to the distribution system before changes or system upgrades are required to safely and reliably integrate those additional distributed energy generation pieces of equipment. So it's essentially looking at the the distribution grid as it stands with no upgrades to it, no additional cost, no additional equipment, and evaluating on a couple different metrics how much, in this case, solar generation can be added. The two big concerns there are voltage rise. So as Kim was talking about before, some of those feeders are quite long in the PPL service territory, on average 27 miles. And it's important to maintain the proper voltage across the length of that feeder. There are ways to maintain that with voltage regulators, but these are expensive, and then that kind of breaks the assumption of hosting capacity because purchasing additional voltage regulators would be added cost. So you have to make sure that adding in these solar generation facilities would not cause the voltage to rise too high. Additionally, backflow protection is the other main concern. To simplify it, the sum of generation across the feeder has to be less than the sum of the loads across the feeder. So if more electricity is being generated on a distributed basis along the feeder than is being consumed, it would cause the electricity to backflow into the substation and trip the circuit breaker, which would be a violation of hosting capacity. So that's the important thing to know there. Keep that in mind as we move on and talk about mapping that.
So since we're working along with PP&L on this project, they provided us a lot of information, so much that we can show you guys today. But what they did provide us is different feeder information up to 337 within the PP&L service territory and their relative hosting capacities at those locations. With this, we were able to kind of map out, and that's primarily what you guys will be seeing today, a little zoomed out so you guys can really get an overall big picture idea of what areas are kind of optimal or favorable through a couple of different areas that we looked into today. So mostly, as you guys are going to see, in this PP&L service territory, a few different hotspots, and Nick and I are going to dive really deep into those hotspots and help what curved a lot of these layers to kind of get all the data to push together and make a really nice image for you guys.
All right, so initially we had simply taken the points from PPL and plotted them, but that didn't really convey a lot of information because some of the points had 0 hosting capacity while some had a hosting capacity of 10 megawatts. So what we did instead was created this heat map visualization of those data points. And what you're seeing here, it's pretty intuitive. You know, the brighter yellow is the higher hosting capacity. And what's important to note is that this map is weighted by the hosting capacity itself, not just the density of data points, which was the big reason to go this route. We had initially tried creating some maps using a program called ArcMap, but it didn't really allow us to have the control over the data that we needed. So we pivoted, we used ArcGIS Pro for most of this. As we look at this map, it intuitively makes a lot of sense, keeping in mind that definition of hosting capacity. So the areas with the highest hosting capacity are those near urban areas, because again, there needs to be enough load along the feeder to use all of the energy that is generated. So Allentown, Harrisburg, Williamsport, all being big areas for high load and correspondingly high hosting capacity. This is a really great way to quickly understand where there is room to build, room in a hosting capacity sense, keep in mind, not necessarily geographic room, but where there is hosting capacity room to build solar farms. But it's important to consider other factors like the availability of space and the land cost. And one of the ways that we needed to approach this was to break this, this very fluid, localized heat map down into measurable chunks, units of land, so that we could then compare those with the land costs in those areas. So Josh, if you'll please advance to the next slide. Here you can see, instead of the local hosting capacity, we're calling this the total hosting capacity. The PPL service territory is now divided into smaller chunks so that we can compare on a 1-to-1 ratio. We put a lot of thought into how to actually break up the land. And what we decided to do was borrow a convention from the US Census Bureau. So what you're looking at are all of the US Census tracts within the PPL service territory. They obviously vary in size. I think the intuition behind the census tract is that each one represents roughly a neighborhood, a similar amount of people that live in that area, things like that. The details of which aren't super important here, but this was a way to use a reliable, credible source for breaking down the land, and it made it very easy to work with in ArcGIS Pro. So what I did was I took the hosting capacity in each of those tracts and summed it. So you can see those tracts that are darker green in color have a higher hosting capacity, whereas those that are very light or beige have either low or 0 hosting capacity. And again, this is it makes intuitive sense with what we were seeing before. There are hotspots near Allentown, near Scranton, and Hazleton. So we'll move on and talk about some other factors.
So the next factor we looked into was some land cost. As you can imagine, a developer who would want to put in community solar is going to look for something that's going to, at the end of the day, not cost too much because they do look at their bottom line. So we had 2 approaches for this. One was to look at real land costs. And so what we did is we jumped on a lot of different websites and we started shopping for some land. And we accumulated a lot of different areas, kind of just broken them up into small different regions, and tried collecting as much of the cost and then dividing it out per acre. So we tried collecting them around 12 to 48 different acres, just as a range. And we looked for open land. It wouldn't make sense to demolish a suburban environment to then put in, a gigantic community solar farm. So instead, we looked at land that was already open and available. Then we also factored out a lot of the outliers, so running a little algorithm on that, and it reduced it down to different areas, which showed the cost per land within that area. So the reason we looked at 12 to 48 acres was primarily just a rule of thumb, as well as a few calculations we did later on. It's usually about 5 acres per megawatt, since the maximum capability that the House Bill 531 allows for is up to 3 megawatts. That's about 15 acres. And it does not say anywhere within this specific bill that you have to have only one community solar farm on a plot of land. So theoretically, you could have 3 different community solar farms on a plot of land. Since we have the maximum capability in one specific section of 10 megawatts on the hosting capacity, it leaves, about 3 solar farms that we could put on one single plot of land, especially if they split up the plot of land on a specific kind of just residential or, industrial splitting up of the land specifically. Once we were able to kind of get out the calculations of the cost, you can kind of see the Lackawanna, the Columbia, or the Schuylkill areas being much cheaper for the land cost per acre. And you can imagine Dauphin, Lancaster, and Lehigh being much more expensive per acre. So it was quite interesting. And this actually then backed up for a lot of the census data that we looked into a little bit later on as well. So this was a real land cost look, but realistically, as you can see, as we dove into it, it's really challenging to take this data and apply it to the gigantic map that we had. So we came up with a newer, a little bit easier method to work with, which is what Nick's going to talk about.
So rather than looking at that absolute land cost in isolated areas that we were able to find real estate listings, we decided to use some proxy data that would not necessarily be as accurate and true to the absolute land cost, but instead an indicator of the relative cost of land. And a really easy way to do that was, once again, using data from the US Census Bureau. They collect data on the median housing value by US Census tract. And again, to be perfectly clear, this is not an absolute measure of the cost of land, but rather operating on the assumption that if the housing value is higher in a certain area, it's very likely that the cost of land is also going to be higher in that area. So we downloaded that data and loaded it into ArcGIS Pro and created the map that you can see on your screen here. Those areas colored in red are the most expensive. It makes a lot of sense. Kind of the wealthy suburban areas around Philadelphia are going to have a much higher median housing value and cost of land, whereas those areas in rural places around Hazleton, around Scranton, Williamsport, a little bit more affordable when it comes to both housing and hopefully land. So this was a way that we could find land cost information for the entire service area, and also it's broken down into those same US Census tracts so we can compare it with hosting capacity.
So the next factor we tried looking into was about irradiance. And as you can see on this map, it looks very detailed in the sense that Pennsylvania has from this image, it looks like it has a very large difference in irradiance levels from one side to another. But if you look really small in the top right, there's actually not that much of a difference. It ranges from about 3.4 and 4.4 all the way from one corner to the other corner of Pennsylvania. And when we averaged the PP&L service territory specifically, it came out to about 4.06 kilowatts per hour per meter squared per day. So all in all, the entire PP&L service territory, which is right here in this section, I don't know if you guys can see the red pointer, but it's pretty averaged the whole time. So we found that it's not very, good of a factor to put into it, knowing that the community solar variability of irradiance is not going to change that much. So we took it into consideration, but at the same time, it didn't seem too important to put it as an extra layer in what we were factoring in. Then we actually want to get out the cost. So how much on earth is community solar going to cost So for most of the figures that we looked at was about 3 megawatts, like we said earlier. And if you're going to build one out, you're going to want it to be as much as you possibly can. And as we know from community solar, everyone is kind of just going to buy subscriptions to it. That's why I like this image on the right. Kind of shows that not that you specifically own those solar panels, but you kind of just get your own little sections of energy that you get to claim as your own. Doesn't mean it goes directly to your house, but you just get credit for it. Since there's a few different ways on how to calculate it, we tried each one of them, and the nice part is we got a nice comfortable range of how much it'll cost. One from a solar irradiance perspective, one from a actual individual solar panel. So as you know, solar panels are drastically different between companies, between different kilowatts that they can bring in. So, and as well as the industry rule of thumb. So for 3 megawatts, we came up with a nice comfortable range of 2,200 to about 3,000 panels are going to be within 3 megawatts. Again, this can greatly differ depending on the overall kilowatts of the panels themselves. And the cost of the panels themselves can range between $600,000 and $850,000. Again, big range, but when you're looking at the overall project of between 3 and 4.5 million, the panels surprisingly aren't the largest cost.
All right, so now moving into the results section of our project, I'm going to walk you through the formula that we used to calculate the favorability of community solar in each census tract throughout the PPL service territory. As Josh mentioned, the variance in solar radiation was pretty minimal, so for simplicity's sake, we decided to exclude that from our favorability calculation. What we looked at, therefore, was the hosting capacity and the median housing value of the tract, which again is serving as a proxy for the approximate land cost. To consolidate both of these factors into one variable, I used the formula that you can see on the screen here. Working with the table functionality of ArcGIS Pro, I was able to calculate an F variable, and I just took steps to kind of normalize each factor into a number between 0 and 1 by dividing the hosting capacity of each tract by the hosting capacity of the tract with the highest hosting capacity. So then, we have a relative measure between 0 and 1 for how much hosting capacity there is, and the same with the approximate cost of land. And then simply we subtracted the cost of land relative number from the hosting capacity relative number, which was an effective way to create this F, which varies between -1 and 1. F would be -1 when there is 0 hosting capacity and it's the most expensive land in the service territory, and it would be 1 when it has the most hosting capacity in the entire service territory and the lowest cost of land. So then we were able to take this F and plot it on a map. Josh, if you'll please advance to the next slide. And this is kind of the crown jewel of our project. This is where all of the data comes together. So you can see that, and again, this is relative community solar favorability. But this really matches up with the maps we were looking at earlier, and it paints a pretty clear story. The areas down near Philadelphia where you're seeing a lot of red, those did have high hosting capacity, but the cost of land is really high there as well. So it's clearly not favorable for the development of community solar. The areas that are pretty favorable are those that are somewhat urban, but not the big metropolitan cities. So Hazleton and Scranton come up as really wonderful areas for the possibility of developing community solar. There's enough load in those areas to have a high hosting capacity. The cost of land was relatively low, and that would be our suggestion for the places to consider building a community solar farm. Obviously, there are some other areas on this map as well, and this map could be made more granular in the future by working with a little bit more data. We could try and make it a bit more precise, but this paints a pretty clear picture of the general areas that are favorable.
So I'm sure you guys have also at some point just asked the question like, well, all because we already know down on the one areas in Allentown and Bethlehem, it's really good hosting capacity. It doesn't mean it doesn't completely rule out that area because the land is quite expensive. Since it is a very developed area, there's a lot of rooftop potential. So what I have is a little snippet of the Lehigh Valley, as you can see on the right image, the larger one. This is off Google Sunroof, and it's not a complete image. They don't have all of their data, but the data they do have shows a very good idea of where rooftop can be. The brighter the areas, the better rooftop can be. The problem is we exactly can't calculate how much it would be for us to put that on top, or the viability of it. We would just have to refer back to the first one of just showing, since it is a more dense urban environment, it would then be more favorable to put it community solar in that area. And because of that, let's assume that there's also an industrial park that could potentially go there. If you imagine an industrial park in this area that has a lot of rooftop space, then putting a lot of solar panels on top of that. And then if they, in that industrial park, have several different tenants that want to use this power and subscribe to it, the House bill states that community solar is anything that has 2 or more subscribers. So if a business is able to have more than 2 subscribers when they put rooftop solar on, then great, they've now become community solar. Thus, it's been able to open the platform up for more people to take advantage of this great opportunity. So the Lehigh Valley, the Bethlehem area, maybe the Harrisburg area as well, all those areas that were in red or in orange that were ruled out because of land cost now can be looked at again in the potential future for just being a great option as well. So one other piece that we wanted to look into was how many solar panels are already out there, how many people already are getting on board with this, and how many are not, and can we make it more accessible overall. So I have this image right here, again, off Google Sunroof, and this is the amount of people that already have some sort of solar installed. This is both industrial, commercial, as well as residential. And you can see, nice dense area down here by the Philadelphia area. It's got a nice good section over here. Or I'm sorry, it's about Philadelphia area, relatively close. I gotta relearn my map. But yeah, you can imagine that in certain areas, there's a good density of where solar already is. But if I switch to the next one, which shows the median household income, that the areas that have the most amount of solar, as we saw previously, are the darker regions showing higher income. So by this, we can deduce that if someone is participating in some sort of solar project or just taking advantage of solar by maybe purchasing it or getting it installed in their house, then we can also assume that this is correlated to a higher income overall. Well, the nice part about the House bill is that it does actually have benefits or some sort of tax reliefs that allows for median or even lower income individuals to take advantage of community solar. So if someone who is living in an apartment complex that doesn't have the ability to get solar on top of their rooftop, or maybe they just don't have the income to be able to really push for it or anything like that, and maybe they're in their own home, they can still take advantage of community solar, not at their own house, but at the same time, maybe get some benefits from the state so that they can take advantage of it, which is a great opportunity overall that this bill is going to allow for. So we got some future work that Nick's going to talk about for the next part.
Yes, so we covered a lot of ground here, but there's a lot of work left to do on this topic. One interesting thing to look at would be diverging from that peer hosting capacity analysis and kind of considering a cost-benefit analysis of building some additional equipment. If you were willing to look at incurring the expense to build voltage regulators or even additional lines that could open up different areas in the service territory as favorable for community solar. Obviously, that would be very costly, but it's something that could be looked into in future projects. Additionally, some refinements could be made of the existing ranking scheme. someone could choose to redo this and include that solar installation, or come up with a way to develop the a metric for the absolute cost of land rather than the approximate data that we used. Finally, someone could consider implementing some minimum or maximum value thresholds. Say that an area must have a minimum hosting capacity of 2 megawatts, for instance, to even be considered. Josh kind of touched on that rooftop solar potential and social equity index. These are both things that could use a lot more research in future projects. And finally, someone could work on creating a dynamic and live updating favorability map. What you saw was very static based upon snapshot data from PPL, but a way to make this even more powerful and useful would be if that map were made live so that it could reflect the changes that occur across the PPL system in real time. So hopefully there is enough interest here for future energy systems engineering students to continue this work and build off of what we have begun here. And with that, we would like to thank you for your attention and try to field any questions that you may have for us.
Thank you, Josh and Nick. And questions? You can use the chat feature too if you don't want to speak. You can send me the questions or send it to everybody.
Hey, Rudy, this is Dave Turner. Just a quick question. Was the project commissioned by PPL to determine whether community solar was viable in their territory, or did they just choose the PPL territory because it was local?
Well, let me answer that, Dave. All our projects, we look for industry sponsors, so it was their suggestion. And we fine-tuned it for a 10-month span at best, So we tailored it so that it serves purpose of educating the students as well as having some real interest to the industry.
Okay. So utilities across the country, we build solar projects everywhere, charge us typically between $100,000 to $1.5 million for line upgrades for solar projects. Depends on where we are. So any of the work that could be done to help understand what is the real cost of the interconnection would be great.
Okay, good point. I know Vince, a former student, had some work done in that area, right, Vince?
Yes.
Yeah, I actually had a follow-up question tying into that. So a quick question for you guys. You mentioned that the hosting capacity values that you used were, a metric based on basically the amount of load beyond generation on a feeder. Did those values, I guess, also account for the ability of a given feeder to accept more generation, meaning that there is availability on those lines and on those equipments in the room on the threshold between their operating conditions and their rating, meaning that our interconnection cost factored into that hosting capacity?
So if I'm understanding your question correctly, you were asking about how the hosting capacity itself was calculated, right?
Yes.
All right. So we actually were not the ones that went ahead and calculated the hosting capacity. That data was provided to us by PPL. Our advisor, Femi, is actually on the call right now. He might be able to offer a little bit more insight into, which factors went into how PPL calculated that hosting capacity. But for the purposes of our project and our scope, we just looked at that as a snapshot. This is what the hosting capacity is, and locked it in as that, and then did our analysis from there.
Hi, Vince. This is Femi. So I just want to give a brief overview of how we came about the hosting capacity. So just like they described, the hosting capacity measures the maximum amount of generation that you can host on a specific feeder without the requirement for system upgrade. So the constraints that were actually utilized, which is what you want, is first of all, there mustn't be a reverse flow, mostly in the condition, at a situation where there's a minimum load on the system, minimum daytime load in terms of solar. So we don't want a reverse power flow back to the substation. The second constraint is voltage. They touched on voltage. However, like the PUC recommendation allows a voltage deviation between 5%, plus or minus 5%. So if there's going to be a voltage rise at all, we don't want that to exceed 5%. So that was the second constraint that was put into consideration. The third constraint is the thermal limit. Just with utility, hosting, load, generation, we don't want to exceed the rating of the cables. So that's a third factor. Some other factors were protection factors, such as some of these renewable sources, especially the inverter connected renewable sources, they had what we know that as every other sources. But their short circuit current, when they come into the grid during faults, might reduce such way some protective device might not trip during fault. So that was also put into consideration. That was a protection rate. So all these factors combined all together, having satisfied them in SIME, built into a SIME software, we're able to run the hosting capacity analysis, which is called the integration capacity analysis for each feeder, and therefore produce what the hosting capacity is going to be for about 1,300 feeders that we have on the PPL system. Thank you.
Thank you for kind of expanding upon that a little bit, Femi. That was a much more in-depth presentation of that than Josh or I would have been able to give, and I'm sure the audience appreciated it.
Thank you.
We have a question from Tony from Con Ed. What is the top community solar state? Any lessons learned on their implementation? You guys want to take it on?
Yeah, it was surprisingly Minnesota, then followed by California. So I didn't anticipate Minnesota would be one of the first ones to get community solar out there, but they did it. And the lessons learned from them, we didn't learn too much from the regulation side of it, but we did learn that they did start off with like just small tidbits here and there, and then it grew to a little bit more. So by tidbits, I mean they didn't go too big too soon with small projects that then helped out. So we're talking like apartment complexes or hotels or things like that. And then things to grew larger and larger for then the suburban environments to then kind of join in and jump into it later. So they kind of dipped their toe into it and then it grew quite quickly.
Good. Yeah, Minnesota has got some very favorable net metering laws favorable towards customers, so it may not be very friendly to utilities. Anyway, any other questions for Nick and Josh? If not, let's, why don't you unshare? Thank you again. And let's see, Larry Montez is team 5. Larry, you there?
Hello.
Yes.
All right, I'm going to share the PowerPoint. Does everyone see it? Well, let me start from the first slide. There we go. All right. Does everyone hear me clearly?
You're good.
Hello, my name is Larry Montes, and the project I'll talk to you about today is integrating phase change materials into concrete. This project was led by Dr. Carlos Romero and Professor Clay Naito in the Atlas Research Building. So the demand for advancements in indoor comfort has increased over the years, and such improvements have led to an increase in energy usage in space heating and cooling. Heating and cooling alone on average accounts for 24% of a building or household's energy consumption. As such, there has been a need for improvements in the efficiency of space heating and cooling technologies. One such method would be to reduce the energy needed to reach desired temperatures, and to accomplish such a task, the room would need to be capable of passively maintaining temperatures near desired conditions without the aid of heating and cooling systems. This can be accomplished using phase change materials. Phase change materials are substances that absorb or release large amounts of energy during a phase change, such as from solid to liquid, it would absorb a large amount of heat. What can be done is to take advantage of this nature by using a PCM that changes phase around room temperature and embedding building walls with it. Through this, the walls will passively heat the room when it's too cold, and the PCMs release energy in the form of heat, or passively cool the room down when it's too hot, and the PCM melts and absorbs large amounts of energy as heat. Such a technology would potentially reduce the cost of space heating and cooling. First, I'll talk a bit about the project from last semester and how it ties into this new project. In the prior semester, the main project I was working on was thermal energy storage using cementitious materials. The project was to design a thermal energy storage system that was capable of operating around 400 degrees Celsius, maintain 90% round trip efficiency, and cost less than $25 per kilowatt hour. For the design, the plan was to have 2 plenum chambers, one on top of the concrete and one below the concrete, as seen in the graph or the figure. And a heat transfer fluid would pass through these chambers and transfer heat to the concrete via thermosiphons that are running through the concrete block. This project is still continuing with the core team. In this new project, we are testing the effects of integrating phase change materials into concrete to act as a passive heating and cooling mechanism. While this current project focuses on using PCM concrete in room temperature settings, the potential for this study is implementing PCM in the thermal energy storage system concrete, as a PCM with a phase change temperature around a power plant's operating temperature would allow this storage system to absorb much more thermal energy per unit volume and increase storage capacity. For the literature review, we first look at PCMs that we possessed and whether or not they had a phase change around room temperature. And then we looked at various papers by other institutions to research methods for experimentation and implementing PCMs into concrete. The best method was by encapsulating the PCMs within porous aggregates that would be inside the concrete. Other methods, for example, simply mixing the PCM into the concrete mixture, led to cracking within the concrete after the PCM changed phase. We then looked at patents that may be similar to our project. However, the patents we found were all abandoned or expired, and other patents that were different enough in design allowed us to proceed. We narrowed down 2 main encapsulation methods for injecting PCM into the aggregates. We first have the soaking method. For this method, you submerge the dry aggregates in a container filled with melted PCM for several hours in an oven to keep the PCM in a liquid state. And you take weight measurements over time to determine how much PCM was absorbed by the aggregate. The second method is vacuum impregnation, which is similar to soaking, except we have the aggregates and PCM in a vacuum sealed chamber to remove any air trapped in the aggregates and allow more PCM to be soaked. Vacuum impregnation has noticeably better results than direct impregnation as porosity increases. So for example, an aggregate with porosity below 30% will see similar amounts of absorption between both methods, whereas after 30%, the vacuum impregnation method performs substantially better. Finally, we researched coating methods for the aggregate embedded in the PCM. Since in liquid state, the PCM will leak out. The most prominent coating methods included immersing the PCM in the aggregate into epoxy, and adding graphite as 15% by weight to the epoxy showed a noticeable increase in thermal conductivity. And another benefit of epoxy coating is that it increases the PCM's resistance to changing shape when the concrete experiences any strain. For the experiments, we performed tests on 2 types of aggregates, 3/4 inch norlite and 3/8 inch norlite. Norlite is a type of expanded shale aggregate. For the PCM, we had calcium chloride hexahydrate, which possessed a phase change temperature at 26 degrees Celsius or around 79 degrees Fahrenheit, which is fairly close to room temperature. For the initial tests, we wanted to run through them using water at first instead of the PCM to make sure we properly executed the procedure and not to waste the PCM and aggregates we had before we were sure about the full experimental procedure. We tested both encapsulation methods of soaking and vacuum impregnation using water to determine the method we would use in the final experiment with PCM. And here are two images of the vacuum method. So here's the vacuum, and inside this chamber, which is vacuum sealed, on the left, we have the 3/4 inch Norlite aggregate, and on the right, we have the 3/8 inch Norlite aggregate. They would be inside this chamber for about 3 hours. After 3 hours, all the air inside the aggregates that were trapped have been removed. And at this point, the water was inserted into the chamber through this tube. And then after an hour of soaking, the rocks are then removed and their weights are taken. So these are the final results of these experiments. So the first test we ran was for the soaking method for the 3/4 inch Norlite and 3/8 inch Norlite aggregate shown above. And the measurements resulted in the aggregates having an absorption around 22%, which means it was able to absorb 22% of its weight worth of water. And then the second test was using the vacuum method, which also ended up with around 22% absorption, which matches the results from other papers we read saying that when the absorption is beneath 30%, you will see both methods have similar absorption percentages. And then finally, we ran an extra test, seeing a method where after we have finished with the absorption, after we have finished with the vacuum method, we let air into the chamber for 30 minutes to push water further into the aggregate. However, this resulted in only a 1% increase in absorption, so it was not very different. I performed a cost analysis of our concrete PCM aggregate mixture to find the space heating and cooling reduction. For this, I estimated PCM performance and cost reductions using other reports and studies, as we were unable to perform our own tests due to the closure of the laboratories in the campus. From the mixture, we theorized certain ratios for a concrete block with aggregate and PCM inside and came to a cost of $22.44 per cubic foot. The household I looked at had a floor area of 2,600 feet squared and a wall area of about 1,500 feet squared. It's an average sized house. According to the studies I analyzed, we would expect an average space heating and cooling energy reduction of about 50% with our specific PCM concrete design. This would lead to an average of about 20% savings on electricity bills. And using a study by the US Department of Energy, I was also able to calculate the payback period, which varied greatly depending on the city heating and cooling electricity prices. And this table shows the different payback period values. So cities like Atlanta that had low costs for electricity for cooling had the longest payback period, but Phoenix, Arizona, that had the largest costs associated with heating and cooling had the shortest payback period. With the cost of analysis reports, it can be further seen how porosity affects the performance of the PCM concrete. One of the reports had divided their analysis based on the percent of PCM by weight present in the mixture and showed this logarithmic trend that we see in the graph. At low porosities, increasing the PCM content substantially improves the savings. However, as we approach 20% and 30%, the savings decrease. And typically you will see no more than 30% because after this point, the cost of incorporating more PCM starts to outweigh the savings. So unfortunately, due to COVID, lab access was cut off when we were ready to begin experimentation with the phase change materials. And while we should expect similar results, we still needed to test the coating of the aggregates with PCM inside. We also still need to test the compressive strength of concrete with the PCM aggregate inside to ensure that the mixture is capable of taking the strain caused by forces on the concrete in a typical setting. We also need to see how we can improve performance by increasing the amount of PCM we use, by potentially increasing the amount of aggregate in the mixture, or by using a higher porosity aggregate. And at this point, I will take questions. Thank you.
Thank you, Larry. Questions for Larry? As before, you can ask the question directly or send it through chat if you wish. Questions for Larry?
I have one, Rudy.
Yes, Cheryl, please.
Has there been any work yet on the effects of the porous material within the concrete in terms of its stability over time? I'm just wondering what kind of chemistry is going on in the walls.
Good question.
As in like how it's like over time as it goes through multiple thermal cycles, whether it can sustain it. Well, you'll really only see huge like effects at really high temperatures, and this is something that will come into play when we're attempting to integrate the PCM into our power plant level concrete. But for room temperature, you don't really see many issues appear over years. I didn't see any reports that specifically were about seeing the effects of this over years, because not many tests have been done that spanned over multiple years.
Thank you.
Larry, I have a question. Your data on Phoenix was most favorable. So any insights into that?
Well, that was from a report done by the U.S. Department of Energy. They looked at those specific states, and in their specific case, they tested multiple phase change materials, and they tested multiple temperatures in which those materials would change phase, and seeing different heat of change, trying to remember the word, specific heats of the phase change materials. And with that, they were able to also analyze the specific cost of electricity at different times of the day, different months. And then another report I looked at specific cities every month of the year, the kind of cost reduction you'd see from the PCMs. So obviously, the more southern states, they experience higher temperatures, and those will see the most favorable performances. But what could also be noted is that on the opposite spectrum, where those studies that you saw, none of them were very north, but the closer the temperature was to the phase change material temperature, the higher the cost savings was. So that's something.
Okay, good. Well, if you don't, can you unshare yourself, Larry? All right.
I believe I've stopped sharing screen.
Good. So we've come to the break, and although we have kind of overshot the runway a little bit, we still have time for the break. And also time for you guys to fill out the evaluation forms, either through Google form or through the hard copy that was mailed to you. So choose either option. The Google form is frankly far easier to kind of navigate and actually get it done right away. So are there any other general questions you want to pose to the students? Anybody? So,
Rudy, it's Al.
Al, okay, go ahead, Al.
When a couple presentations back, when Nick and Josh were talking, I'm not sure where it was, but somewhere on the line, my internet kept cutting out, and I didn't hear everything. So if this is a repetitive question, I apologize, but I believe early in Nick's part of the presentation, he said something about restricting power flow up through the subs. Was that a condition that was placed by the state, by PPL, or your study team? Because obviously the technology exists to let that happen, although modifications to the feeders are clearly necessary at some expense.
So I can jump in and answer that. That is kind of a restriction that was placed by the fact that we were using hosting capacity as the basis of our analysis. In order to fall within the realm of hosting capacity, there cannot be any modifications or upgrades made to the existing equipment. So like we had mentioned towards the end of our presentation in future work, that would definitely be something that could be considered in a cost-benefit analysis, future work of whether that expense would be worth it. But that was, it was not included in our project scope because that would be outside the definition of pure hosting capacity.
Oh, okay, thanks, Nick. Good point. One other question I had during your presentation, and either you or Josh might be able to answer it. When you're talking about these areas that have the highest capacity and also it's obvious the higher populations, obviously if you put it on roofs, I don't think most places have too many restrictions on that, but if you had to put it on vacant land, do these municipalities have any zoning restrictions or building restrictions about such use of open land?
Yeah, that was one piece that we looked into when we were trying to get the land cost, because we had to find industrial property. I forget exactly how they define it, but it had to be defined as something that was industrial to meet these specific type of restrictions. That was just easier for us when we looked into it. So as long as it fell into the category of industrial, it then already had all the municipal I would say approvals, whereas a residential, if it was then vacant, it would then it'd have to go through a few extra steps converting the land type.
Okay, thanks. Yeah, that kind of adds a little clarity to it, because like cities like Allentown and Harrisburg, for instance, probably have very little open land within their communities that are zoned industrial. So you'd really have to take it outside of those into the more suburban areas, most likely.
Jim Gallagher. Similar comment on that presentation, was just to find a way to incorporate community acceptance into the analysis. So you don't end up, putting solar farms where it might be cheapest, but people don't want them. And I'm not exactly sure how to do that, but I think that would be a really beneficial added feature.
Yeah, absolutely. Thank you. Yeah, we appreciate that.
And if I'm not mistaken, Josh, the community solar bill, the way it's shaping up, and I don't know what the status is, it kind of has something for everybody, where investment, different income levels is very favorable.
Yeah, it has a very nice compensation marked into the bill already. So it primarily outlines just the person's income, but how it then is pushed, I believe, is then based on the developers. Once it's approved, developers will then take on those projects, and then I guess their marketing teams will be the ones to go forth and convince everybody that it's great.
Any other question for anybody? So hearing none, I thought, why didn't you, if you're still working on the evaluation form, please go ahead and complete it. It's a great way to get feedback because their job as they go into the outside world is getting people to buy their presentation. And so they need to cover a lot of territory just as a way of how much time the students have spent, COVID or no COVID. I think it averages almost anywhere from 600 to 1,000 hours over the 2 semesters. So they've done a lot of work, hit some bumps on the road, many bumps on the road, dead ends sometimes. And so it's kind of a culmination of something that they've experienced in real life. So hopefully it was a good experience for the students. And somebody has his hand raised there. Oh.
I was waving at the neighbors.
Oh, okay, sorry. That's good. That's another part of this virtual learning is all sorts of interesting things. Let's see, on the chat, if you haven't received your evaluation form, hey, Susan, send a note to Susan and she can at least send that over to you, but it was sent in the package to all the, are there people who have these evaluation forms or can get them, or? There was one in the chat that requested it.
Hey, Rudy, this is Dan Chapley.
Yes.
Just a quick question. How do you want us to send these forms back? Because I tried opening up that form in Google Docs and it really doesn't seem like it's a fill in the form type of a thing that you could do. I mean, I have it filled out on paper, but is there a way that you could, that you know of, that we send it back to you, or do we just scan it in and send it back? How do you want to have it sent back?
All of the above. Google Forms allows you to fill it electronically and it does the rest. So when you say you can't do it, there's a...
Well, when I have the document from Susan, how do you open it up? Because I opened it up, downloaded it, and it became a document, but you can't fill it in.
You shouldn't have to download it. You should just click on the link and it'll take you right to the Google document. And then all the buttons are there. It's the exact same form that you have on paper. It's just nicely more laid out, and there's spaces for comments for you to write in for each team member that spoke.
Okay, I'll give that a try. Thank you.
Yeah, it's nothing you have to download.
Okay. Yeah, the Google form is probably the most convenient to work with. All right, so why don't we take a break before the next meeting? This will be an advisory council meeting. And I'll leave the connections open so you don't lose it, or you can take a bio break or get a snack, or if you want to get a glass of wine or a beer, go for it. All right. Hearing no more questions, the students, you guys are excused. Thank you again for participating.
Thank you to all of our visitors. Really appreciate your participation.
Thank you.
Thank you, everyone.
Thank you.
And we will have class next week, same time.
Rudy, how long did you say the break is going to be?
We will convene, we'll start up in another 19 minutes.
Okay, sounds good.
And for those of you still here, I did double check it. When you get to the Google form, you click on the link and then you fill your name in and then your email address. And then underneath that, there's a next button. You click next and that will take you to all the students' sections. It's all broken out by each student that spoke.
Susan, can you reset that?
Yeah, I'm sending it to you right now.
Thank you.
I just wanted to get that in there before I miss
Thank
everything.
you.